All right, welcome back to algorithm analysis. So, we had a cute little example that involved some 41 knowledge, and we got that. Let's keep going. I talked about some symbols. We know big O. There are some other ones to talk about too. So let's finally learn once and for all the mathematical definition of big O. Like, what does it really mean when I write O of n squared? O of n. All right. It's talking about the asymptotic growth of a function, really. So here is the syntax and the real math. All right, so we say that f is equal to big O of g, and the equality sign is unfortunate. Like, really, it should have been like f is in big O of g, because it's an equivalence class. We read it like this. We say f is big O of g, even though we write it with an equal sign, or f is O of g, or f is big O of g. That's how you write that and speak it. And then you remember from 41, essentially the definition of what big O means. It's like g bounds f. Yeah, f of n is always smaller than g of n if you drop a bunch of constant factors out in the front and like you cross those off, and like you only worry about giant values of n and things like that, right? And if there is only a constant, like if you always have, no matter the input, a constant amount of work to do, like f of n is always 5 things to do, then you can bound that with the function 1. And that's really a function, O of 1. You say that it's constant time O of 1, which just means like define g to be the function that takes any input and returns 1. So that's how it's talking. That's what that means. And here's the real definition, with a pretty picture to go along with it. So here's the real definition of big O mathematically. Let's pretend that f and g are two functions. They take numbers to numbers. They take positive integers to positive reals. All right, that's the setup. It's like, this is like your input size, and this is like the output of the functions is like how much work needs to be done to work on that input size, for example. But this works for anything. It's mathematical. It didn't have to be about programs. Then we say that f is big O of g if this is all true. If there exist two constants, c and n naught, such that f of n is less than that constant times g of n. Like, this is true. F of n is less than c times g of n whenever n is greater than or equal to that n naught. All right? So that's mathematically what it means for f to be big O of g. If you can find these two constants such that for every n greater than n naught, from then onwards, f is bounded above by a constant multiple of g of n. Okay? So that is weird, and this picture kind of explains what's going on better, I think. So here is your function f that you're trying to model. I'm trying to figure out the complexity of f with hopefully an easier amount of letters. All right, it's O of some easy thing like n squared. But f is kind of wonky. F looks weird, and that's unfortunate. But here's like g. Here's g of n times some c. Like, it's been scaled. So like here's like the original function. Here's a constant times that function, right? It grows a bit faster but looks the same. So here's a constant times g of n for some constant. You notice that if you pick the constant 42 or something, this is what g looks like when you multiply every answer by 42. There is a point at which, and the point we're going to call n naught, there's a point at which c times g of n is always above f of n until the end of time after that. It might like mess around at the beginning, but eventually at n naught, from then onwards, c times g of n always outgrows f of n. So instead of talking about f of n, you can say that's O of g of n, and that gives you an idea of how fast f works, how fast f grows. So this is saying that g is an upper bound for f. You multiply g by some constant, it becomes an upper bound. It's always bigger than f of n, okay? So, for example, f of n, like here's your function f. If that's equal to 2n squared, it's big O of course, n squared. It's big O of n cubed. It's big O of n to the 4th. So these all work, but usually you prefer the smallest one. So f of n, like this function, 2n squared, it's big O of n squared, it's big O of n cubed, it's big O of n to the 4th. The reason, for example, that this is O of n squared is that, like, you can define a g, right? G has to be n squared, and set c to be the number 3, because now you have 3n squared. You see that? The constant is helpful here. It's like you can make it bigger than it used to be. So just pick that constant. It works out that n squared, if you multiply it by that constant everywhere, 3n squared will always win out against 2n squared. And so just n squared, because the constant doesn't really matter in the notation, 2n squared is O of n squared, we say. That's why we can chop off the 2. That's mathematically why we can chop off the 2. And then obviously if n squared is the start, n cubed is always bigger than that, so you can say that this is also O of n cubed. It's also O of n to the 4th. You have many options with big O. It's just, it has to be an upper bound multiplied by that constant from a starting point, from then onwards. Okay? So that's weird and mathematical. Hopefully it makes a little bit of sense, though. I'm going to give you several examples. So let me give you some intuition. Like, why do we, who came up with this idea and who defined this? Like, why do we care about this particular idea? Hopefully, like you've seen from 41, like this concept is helpful in classifying different functions. But like, why did we discover this? So let me give you some more intuition behind what big O means. We say that the function f, it's bounded above by g up to a constant factor asymptotically. All right. So for example, f of x, let's define that to be 2x squared. And we say that f is O of x squared, right? You can chop off, remember your rules, you can chop off the constant factor out in front. And the reason why is that these two functions, they don't look very different when you zoom out. And we care about when we zoom out, right? When n gets large. So let's use the graphing calculator website. F of x is 2x squared. And then g of x equals 2x. No, sorry. I put the 2 in the wrong spot. Just x squared. So we say that f is big O of g, and g is just x squared. Because when you zoom out, zoom out long enough, they're all on top of each other. There's no difference. See that? That's the idea. So that's the point. It's like you could have just said x squared, and I understand. It's very close. It's very similar to x squared as things get large. All right. An alternative definition, if you've taken calculus, and maybe you're actually required to take it before you take this class, I have no clue. But another way to talk about this, if you've seen this notation before, is that f is big O of g if this limit does not blow up. If you can divide f by g, like g is supposed to be bigger, right, an upper bound. So as n gets large, as n approaches infinity, g wins out and keeps f small. It keeps it smaller than positive infinity. See that? So g is able to bound f so that that ratio doesn't get huge. That's another way of defining big O. Some people prefer that way. Those are equivalent ways, though. All right? So that's hopefully some more intuition that's slightly helpful. All right? But at the end of the day, as a computer scientist, you just remember these rules and it all works out. Here's how you calculate big O for the tightest possible bound. Like we get the n squared. N squared is more important than n cubed, even though those are both right answers. We care about n squared for big O for this example. That's the closest one. That's the smallest possible one. All right? And so to get the best possible bound, the tightest possible big O bound, here's your rules, remember. All right? Here are the rules to find a g for the following. And we'll also prove that it works. All right? Here's an example function. Like we count that our function uses, for an input size x, it runs 2x squared minus x plus 3 lines of code, for example. That's what we care about. And so we would like to calculate, like, what is that big O of? And immediately, right, the answer is supposed to be that it's big O of x squared, because you drop the lower order terms. So you drop the minus x and the plus 3, that's the biggest term right there, so it's 2x squared. And then you drop all the constant factors in front of your largest term, so you drop the 2 as well. And so you're left with x squared, and that is the thing that you're working with. All right? So let's give c and n naught for this one. Let's just prove it under the definition of big O. Like, we have to pick a c and an n naught and prove that this always works out. Let me show you that. So, for example, like g, f is big O of g, and g of x is x squared. And the reason this works, the reason x squared can bound this above, is we can pick a constant, let's say 3, c equals 3, and that will give us 3x squared, right? And we just have to prove that 3x squared is always bigger than n squared from some point onwards. And so, like, again, the name of the game is f looks weird. We'd like to model it with, let me draw that better. F looks weird. We'd like to model it with some, maybe g. That looks slightly nicer. And we need to show that, like, this is f. We need to show that from some point onwards, and that point we call n naught, that c times g always bounds above. It's always an upper bound for f, okay, from then onwards. And so I'm going to show you that, like, let's find the point at which 3x squared is bigger than this weird thing. So I think it's, I think it can just be like 2 or something, because f of 2, for example, let's just plug it out. It's 4 times 2, so 8, minus 2 plus 3, which is equal to 8 plus 1, so 9. And then c times, and c, remember, we're choosing to be 3, c times g of 2 is equal to 3, right, because the 3 is out in front, 3 is c, and then g is just x squared, so it's 2 squared, which is equal to 4 times 3, which is 12. And then already, like, and then from then onwards, I think you can imagine that it's always going to be bigger. So that outgrows it, and so we can choose n naught to be 2. And from then onwards, I think you can use fancier math to prove this to yourself. But from then onwards, for any value of n, c times g of 3 times x squared is always going to be bigger than this from 2 onwards, for example. Okay? And so that's why, that's particularly why f of x is O of x squared. And remember, it's not O of n squared if you're using x as the variable. This one's using n, though. Let's try this one now. So, okay, f of n is equal to 5n times log base 2 of n plus log base 2 of n. So again, following the rules, drop all the lower order terms. You have to think about this for a while, but this is like n times a logarithm. That's bigger than just the logarithm by itself, right, as n gets large. So this is the lower order term. We chop that off. And then we chop off constant factors. 5, we have this left, right? 5 is the only constant. N and n log base 2 of n, those involve n. You cannot chop any of those off, even though, like, n is the bigger of the two. They work together. That makes something bigger than n, and bigger than log base 2 of n. Their multiplication gets bigger. And so we say f is equal to, f is big O of n times log base 2 of n. And to say this quickly, like, this is the time complexity of your standard sorting algorithms. This is n log n, we say. Okay? But that's the idea. That's the process. One last one. F of x is this giant thing. So again, drop lower order terms. Which is the highest term here? You might think that this is large, but as x gets huge, again, this is puny. We're talking about giant values, as big as you like to think about. Okay? So that goes away, that goes away, that goes away, and it's 3x42. That's the thing that's left. And then finally you drop the constant factor. So this is f is big O, and what's the variable? The variable is x, big O of x to the 42. All right? So that's how you do the process, and this is going to give you the tightest possible bound. Like, it's also O of x to the 43, but we don't want that one. That's a worse analysis. This is the tightest possible bound, and that's us following the rules. Okay. Again, let's do another example and use the definition. Use that definition. It's important. All right. So let's pretend that this is our function. F is equal to 2n cubed minus 4n squared plus 7. Let's prove that, like, if you follow the rules, of course, f is n cubed. It's big O of n cubed. Let's prove that it is that using our definition. Okay. So we need to find a c and an n naught. Like, if you go back here, you need to find a c and an n naught such that for all values bigger than n naught, from then onwards, c times g of n outgrows f of n. All right? So we need to find some constant to put out in front of n cubed, and just to make it work. All right? So let's pick our, like, the constant can be anything. I think it could be anything bigger than 2, honestly. Well, let's, just to make it fast, make it work quickly, let's pick our constant to be 13. Okay, why not? And let's figure out when because now we're comparing this thing to 13n squared. That's going to be our function, because this is our g, and we're multiplying it by our constant c, which we're choosing to be 13. You can choose it to be anything, as long as you show that it works. We need to prove that f is big O of n cubed. So we need to prove that 13n cubed is bigger than this from some point onward. So now we need to find our n naught, okay? And at that point, we have proven it. So 2n cubed. And also, an easy way to get the 13, let's not even start there. Like, I chose that for a reason. Let me show you how I even chose that, okay? Here's a very easy way to find some constant quickly. That will always work, right? So you start with your original function, 2n cubed minus 4n squared. If you need to mathematically prove this, here's how you need to do it. Think about this. This is a bunch of, this is n cubed, this is n squared, this is a constant. These are all smaller than n cubed, right? So let's just, I don't know, let's make them bigger. So like this is a minus, let's make that a plus. This is immediately, right, less than or equal to 2n cubed plus 4n squared, assuming that these functions are from positive integers, so you never have to worry about negatives. So this is always bigger if you change the minus to a plus 7, so that's fine. And then also, these terms are all smaller than n cubed, so let's just make them n cubed, right? This is 2n, this is always less than or equal to 2n cubed plus 4n cubed plus 7n cubed. Just put an n cubed next to all of these. You see that? And this will always be true. This will almost always be true. Like this is bigger than this. Technically, this one's bigger when n is 0, right? Because then you have the 7 and it wins out. So as long as n is greater than or equal to 1, this works. Works when n is greater than or equal to 1. And so honestly, what is this but 4, 6 plus 7? That's 13 n cubed, and we've just determined that 13n cubed is bigger than the original function whenever n is greater than or equal to 1. So we just found our constant, our c, and we also found our n naught. So c is 13, and n naught is 1, and you see mathematically how that worked, I hope. We found our constant, we found our n naught, and this is just n cubed. Put that out in front, that's our g, and that QED proves that this function is big O of n cubed. We found a way to bound it. We found that these constants work, and we've proven that, right? This chain of inequalities proves that these particular values work, according to the definition of big O. Okay? I hope that makes some sense. Let's see here. Yeah, again, let me show you that, like, once you know that's big O of n, you also know it's O of n squared. Like, that one works immediately. Okay? So let's prove that in general. So it's like you can always go bigger, but you don't usually want to, because that's losing information. So let's pretend f is a function, and its domain is the positive integers, target is the positive reals, as you need for those definitions of big O. Show that if f is big O of n, then f must also be big O of n squared. All right? And so this is your standard direct proof. This is your assumption. Assume this. Assume, and then we assume this, and then we show this. Right? This is what we need to show. All right. So yeah, it's really just going to be unfold the definition. So if we know that f is big O of n, right? Let's assume, let f be big O of n, then, right, what do we know? According to the definition, we know that there exists a c and an n naught. There exists a c and an n naught. I'll use st for such that for every value n greater than or equal to n naught, we have that f of n, right, is less than or equal to, it's bounded above by c times g of n, when g of n is just n, c times n. That's the first thing, okay? So here's the proof. We're going to keep the same c, because we need to show that n squared is also bounding it. Keep the same c. All right? What we need to show, right, we need to show that f is O of n squared. So we need to find a constant. Let's pretend we're using the same constant. We need to find a new n naught, some n naught, call it n naught prime, We need to show that there exists some n naught prime such that, right, f of n is bounded above by c times g of n this time, which is going to be n squared, c times n squared. And this is for all n greater than or equal to this n naught prime that we're picking. Here is the first fact, if we notice this. If, this will lead to the proof, if n is greater than or equal to 1, right, c times n is always, right, is always less than or equal to cn squared, whatever the c was, yeah? C is supposed to be a positive number anyway. This is always true if n is greater than or equal to 1. And let me show that to you, all right? That's going to be important. So, let's see here. So, how can we prove this? C times n is always less than c times n squared, if we know that this is true, n is greater than or equal to 1. So, if n is greater than or equal to 1, that's the same as writing 1 is less than or equal to n. We can multiply both sides of an inequality by a positive number and keep it, so that if we multiply both sides of this by c, we get c times 1 is less than or equal to c times n. You can multiply it by n now, n on both sides, because n is supposed to be a positive number. Ooh, and then we get the inequality, c times n, right, multiplied by n on both sides is less than or equal to cn squared. So we just showed this. And this is going to lead to the answer. This will lead to us finding an n naught, all right? So let's see here. Therefore, this is finally the answer. F of n is equal to, f of n is O of n squared, we say, using, from the definition we need a c. Let's call that c prime. C prime, the new c prime for this one that we're showing, that's the old c. And let's choose n naught prime for this definition. Let's choose that to be the maximum of whatever the old n naught was and the number 1. And this is going to prove it, because if n naught was large, then obviously n is bigger than 1, n naught is bigger than 1, and this inequality holds. And that's what we needed to show that this, we know this, we're showing that it's also less than cn squared, right? We're starting from this, we're assuming this, right? That's our assumption. So f of n, we're assuming that it's less than c times n, and we're showing that it's also less than c times n squared. See that? And that's what we prove. So if n naught is huge, it's already bigger than 1, then this holds. And so if we have this, we know immediately that it's less than c times n squared, which is exactly what we need according to the definition. Okay? Otherwise, if n naught is smaller, if n naught is like 0.5 or something, then this only works. This inequality only holds when n is greater than or equal to 1. So if n naught is not already 1, if it's smaller than 1, it needs to be 1. So let's just choose the maximum of the old n naught and the number 1. That will be the correct n naught to ensure that this inequality holds no matter what. Okay? Because the n naught worked for this one. If it was big, keep it. Otherwise, if it was small, make sure it's at least 1, because we want to make sure that this goes through, because that will give us f of n is less than c times n squared, which proves that it is n squared. Okay? There's a lot of symbol pushing there, and I hope that you saw how that worked. Please yell at me if you have any questions about that. It's a more involved question, that's for sure. But that is the answer. That's going to prove that f of n is O of n squared. All right? And then now, I have a chance for you to try. All right? So here is, again, the definition of big O. You can find these two constants such that for all n greater than n naught, f of n is bounded above by that constant times g of n. And g of n is the thing you put between the parentheses of the O. Here's my question for you now. Let's pretend that f of n is this function. It's n over 100. Prove that it's not true that f is square root of n, because that's n to the 1/2, right? This is essentially, this is O of n, right? Prove that it's not true that f is square root of n, because that's smaller. It can't be bounded above by that, all right? And my hint to you is try using proof by contradiction, which means assume that like the opposite's true, and that will lead to a contradiction, and that should help you, all right? So see if you can figure out this answer. Prove that it's not true that f is square root of n. big O of square root of n. It can't be. It's at least, at least big O of just n, because that's 1 over 100 times n, and that's a constant. So give that a try, and then I'll show you my way. All right, so if we're doing proof by contradiction, we're going to assume that this is not true, right? Assume that this entire theorem is false. We're trying to prove that it's not true that this is true. So the negation of that is prove that it is true. Let's assume that f really is big O of the square root of n. So that's the first thing for a contradiction. Assume f really is big O of square root of n. And that's going to lead to the universe exploding or something. We're going to find a contradiction from this. So what do we get from this definition? We know that, well, it's big O, so there exists a C and an N naught such that the original f, n over 100, I guess, let me write it like this and then explain it. Such that f of n is less than or equal to c times square root of n, because that's g of n, right? G of n is that, for all n greater than or equal to n naught, and f of n is, of course, n over 100, okay? So we know that n over 100 is less than or equal to c times square root of n for all n greater than this n naught that we assume we have, all right? So we know that this is less than or equal to this. We can derive a contradiction from that. So n over 100, if we know that that's less than or equal to c times square root of n, well, we can get rid of the 100 by, or at least on one side, by multiplying it. So let's do times 100 on both sides. That gives me n less than or equal to 100 times c times n. 100 times c times, the square root of n. Now, let's divide both sides. This is the new inequality. Let's divide both sides by square root of n. You can take one out, right, from each side. So let's divide both sides by square root of n. Because what is this but n to the 1, and this is n to the 1/2. So you can divide both of them by square root of n. You can take them out. So this is saying that square root of n, because n, first of all, right, n over square root of n, that's equal to square root of n. N over n to the 1/2 is equal to n to the 1/2. So that's square root of n on the left now, less than or equal to 100 times c, and that's the trick, all right? Now if we square both sides, how do I want to do this? Square both sides. Square root of n squared is n. This whole thing squared is 100 times c squared, whatever that is, some big number, all right? We have just derived that fact. We know that if we assume this, we can end up with the idea that n is less than or equal to 100 times c squared, all right? But, I hope you notice this, c is a constant. It's a giant number maybe, but it's fixed. It's like 42. Is that always multiply a constant by 100 squared? It'll be big for a while, but will it always be bigger than n? It will not, right? That's impossible. N will eventually get large. But c is a constant. It can't grow faster than the parameter of our function because it stays still. It is a constant. And n can be as big as we like. But n is a constant. That's a contradiction. Therefore, it must be the case that the opposite was true. It must have been that f is not big O of the square root of n. And we know that, right? It's O of n at the very least. Okay? I hope that made a bit of sense. So that's a fun idea. That is some practice with big O notation. And now I want to talk about the other two symbols. You have big omega and big theta to go along with big O. And let me show you big omega first. It's kind of the opposite of big O. It's whereas big O is saying, hey, here's an upper bound, big omega is saying, here's a lower bound. It grows no slower than this. All right? So here's how you write it. F is big omega of g if, again, there are constant c and n naught, as usual. But this time, the inequality is flipped. F of n is greater than c times g of n when n is bigger than n naught. Okay? That's the important part now. We've flipped the inequality. This was big O. This way is big omega. All right? And so this is saying, eventually, like they're all wobbling around, there's an n naught. there's some point from then onwards that C times G of n is always smaller than f of n. It's a lower bound. Do you see that? G is a lower bound for f. And so, for example, getting us some notation use, f of n, let's assume that that is 2n to the fifth. This is big omega of n to the fifth, because you can just like choose the constant to be 1, now it's smaller. Or you can pick smaller powers. That's big omega of n to the fourth, big omega of n cubed, because that's growing slower than f of n. You see that's the opposite. Now g is on the bottom. That's big omega. These are now lower bounds. And I hope that makes a little bit of sense. So that's big omega. Next comes big theta. Big theta is in the middle. It's both big O and big omega at the same time, if that makes sense. So that legitimately is the definition, though. We say that f is big theta of g, if and only if, then f is big O of g, and also f is big omega of g. So that means, right, g is an upper bound and a lower bound at the same time, okay? And this is the most useful of the three. Big theta is what we really care about in computer science. So if you spell this out, it's saying, all right, it's big O and big omega at the same time, so there must be two constants, right? One for the big O part and one for the big omega part. There must be C1 and C2, and an n naught, just choose the bigger of the two, such that C1 times g of n is bounding f below. It's smaller, that's the big omega part. And then C2 times g of n is the big O part. It's bounding f above whenever n is greater than or equal to n naught. So from some point onwards, pick a point. Here's our f. Here's C1 times g, and here's C2 times g. From n naught onwards, g is both a lower bound if you use C1, and an upper bound if you use C2. See how it's like sandwiching f in between them? And this is the same g, it's just two different constants. Isn't that nice? So g is both an upper bound and a lower bound for f because of this, and we say that it is the tightest possible bound. All right, that's usually the one we really care about. All right, so this means that there's only one answer. I've been giving you a few answers for these big O's and big omegas. There's only one answer for big theta. It's if you have f of n, 2n to the fifth, it is only big theta of n to the fifth. Cannot be any different. All right. Cannot be n to the fourth, cannot be n to the sixth, because one of these big O's or big omegas ruins the day. That it can only be when it's the same, all right? That's the tightest possible bound. And f, if you have this function, 2n squared, that is only n squared, only big theta of n squared. You have no other option, okay? And instead of writing an extra little dash in between our O's, we usually write big O and we say big O, but anybody who's asking you anything about your algorithm's complexity is really asking you for big theta, even if they say big O, all right? So if somebody says, what's the big O time complexity of this algorithm in an interview, they are asking what is the big theta time complexity of this algorithm, because obviously you could just say like, oh, it's big O of 2 to the n, some giant factor, some horribly fast-growing function, and it would be correct for big O, but you wouldn't get the job, okay? The interviewer, everybody who is using this notation is really asking about the tightest possible bound. So when you see big O, usually you're talking about really big theta, and these rules are going to give you big theta, okay? So that's the goal there, that's the idea. And so with that in mind, here, you try. Here's a few of these. Please find the growth rate of each function, and find a function g such that f is big theta of g. Find the tightest possible bound for these, please. And the trick really is, if you just use these rules all over again, they're really giving you big theta. We said that they were big O before, but it's really a big theta. Okay, so give that a try, and let me show you my answers now that you've tried. So again, drop the lower order terms. The log of a log, I think, is smaller than a normal log, so that's fine. And also n times log of n, and n is like helping that grow large. So 9n log n is the biggest term, and then we chop off the constant factor in front of that. So this first one is big theta of, and by the way, in math, this is a lowercase theta when they're connected. This is a capital theta when they're disconnected. So maybe you know lowercase theta from another math class. This is capital theta. Big theta of n log of n, and I think it was log base 2 of n, whatever it was. Okay, so that's that one. What about this one? N times log base 37 of n. Let's see. Well, this, you have no constants to factor out. Like, these are both involving n. You can't get rid of any of them. So it really is, immediately, big theta of n times log base 37 of n. But actually, the base of a logarithm doesn't matter, because that's just, there's a constant difference between log base 10, log base e, and log base 37, isn't there? The base doesn't matter, so you can just write it n log n and nobody cares. That's why I didn't specify a base here even. Base doesn't matter. So that's a fun fact. You can just say, like, what is, like, log base 2 of x? That is, you can change that to be log base 3 of x, right? That's equal to log base 3 of x by an appropriate different constant, right? It's like times that by log base 2 of 3. And now these are equal. Like, you can relate log base 2 of x and log base 3 of x with a constant, and that's something you can chop off in big theta notation. So it doesn't matter. And we just say log instead of specifying the base, because it really doesn't matter. Isn't that cool? This is a constant. And we can get rid of those. So that's why you can just say n log n. But if you wanted to be precise, you could say log base 37. All right, what about this one? Which one is the smaller factor? If you think about this long enough, if you graph this, it's this one that's going to win. N to the 21, let's say x to the 21. And then this is going to be 1.1 to the x. For a while. Oh gosh, I don't know how to properly do this. Maybe I'll have to... Can I zoom these out quite a ways? Let's make this like 10 and 10 or something. There we go. Here's g of x. It's still small, it's still blue. But look at it. Look at it grow. And eventually, if you zoom out big enough, I promise there's a way. It does end up working that for a big enough value. Oops. Let me show you in Python, because this is important. Here is, let's define f of, like, okay, how about, I don't know, f1 of n to be n to the 21st power. And then let's define f2 of n to be 1.1 to the nth power. Star is power in Python. So f1 of like 45 is 45 to the 21st power. f2 of 45 is still quite small, but I promise that when this gets big, like 45 e to the 10 or something, oh gosh, that'll never give me an answer, will it? 4500? How about that? And f1 of 4500. This has 186 digits. This one has less than that. So even this small growing thing, it's an exponential time thing. That's the bigger one. Okay, so you can chop that off and say big theta of 1.1 to the n. That is not a constant you can get rid of. It's like, you can't just say that's 1 to the n, because that would just be the number 1. Like, the 1.1 is important there. You have to keep it. All right, and then finally this one. That's the easiest of the three, or of the four. Lower order term, lower order term. It's big theta of n cubed. I hope you see that. So, yeah, that's getting us some practice with all that stuff. Yeah, for the final trick, I have one more question for you to try. Here is a function. F of n is n cubed plus 3n squared plus 4. Please prove that it is big theta of n cubed, right? So that means you're going to prove that it's both big omega of n cubed and big O of n cubed. And that's going to involve finding constants. You better find those constants, pick an n naught, and you better show with math that the functions like sandwich, like n cubed multiplied by c1 and n cubed multiplied by c2, those sandwich for the c1 and c2 that you chose, they sandwich this function in between them as n gets large enough and past an n naught value. Okay, so here's the definition of big theta again, if you want to stare at that. but see if you can prove this. Find those values, prove once and for all, so that you don't have to, you can just use the easy theorem, the easy result. Just follow the rules from then on. But I want you to understand mathematically why it all works first. All right, so do it the hard way, and then you can do it the easy way from here on. So we have to show that n cubed is a lower bound and an upper bound of that f function. So let's do the lower bound part first. So this, we need to show that n cubed is smaller than this, essentially. Some c1 times n cubed, right, because that's our g. We need to show that that's smaller than n cubed plus 3n squared plus 4, all right? And this is always true, right? Even if c1 is 1, just n cubed, it's smaller than all that because these are extra. That's giving you bigger things. So if you just choose c1 to be 1, this will always work even if n is 0, from 0 onwards. Like, no matter what, this works. So that could be our n naught, maybe. That words works for when n is greater than or equal to 0. Do you see that? So this is a first constant, and this is a first n naught, 0. Like, that's going to work. So that is, therefore, it's big omega of n cubed. And now we need to prove the flip side, that this is smaller than some constant times n cubed. So we have the other way around. And here's how you do that trick that I showed you from before. So you start with this, 3 and the original function, n cubed plus 3n squared plus 4. And then you take all these, if they weren't negative, make them positive, and then change all these smaller terms to n cubed. It'll make it a bigger function, right? This is, we need to show that this is less than or equal to c2 times n cubed. And again, if you just take this, copy it, this is less than or equal to, assuming n is greater than 0, it's at least 1. If you just change all these n cubed, like that one's already n cubed, change this n squared to n cubed, 3n cubed. It'll make it bigger, right? N cubed. Plus 4 times a constant, times 1, make it times n cubed, 4n cubed. See that? So that's bigger whenever, right? This only works, this is true when n is greater than or equal to 1, right? Works when n is greater than or equal to 1. That's always true. And what is this but 1, 2, 3, 4, 8. 8n cubed. And that can be your next constant, c2. And this works whenever n is greater than or equal to 1. And then you need to just choose like the bigger of your n naughts. Like this one works out when n is greater than 0, greater than or equal to 0. This one's only working when n is greater than or equal to 1. So for your theta, your big theta, just use the bigger of the two. And by the way, this bottom part proves that it's big O, therefore big O. And so what you do is you say, all right, c1 is equal to 1. c2 is equal to 8. Oops. And many different values work, by the way. These are just the ones that it's easiest to show. And then our n naught, that this is always going to work for, well, it's got to be bigger than or equal to 0, and it's got to be bigger than or equal to 1, so we'll just pick 1, the bigger of the two. So the n naught for both of them, just choose that to be 1, and therefore the whole thing is big theta of n cubed, QED. Does that make sense? I hope that's what you got. Very, very common thing that you're going to want to be able to do, to mathematically specify whether or not a function is an upper bound or a lower bound, or, for the case of big theta, both. All right, so that's the last question I have for you for the day. I have just 2 more slides, and then we'll wait for the rest next time. All right, let's talk about complexity, finally, of algorithms, because this was just functions. Like some arbitrary mathematical function. It didn't have to talk about a program, it's just something random. Well, let's talk about how to figure out the complexity of our algorithms, the programs that we write. All right, so there are many different kinds of computational complexity. That's what we're after in this class, right? We need to figure out how complex our programs are for some sense of compute time, power, memory, different things. So computational complexity is just an umbrella term for the amount of resources used by an algorithm. And resources is a generic term, right? It could be anything. It could be time, it could be space. Those are things that we've talked about before in 41, right? So there's a bunch of different kinds of resources. Power is one that we haven't used before, but you could totally do it for power. So we need to get even more specific. We have time complexity. We say that that is the amount of time that a program needs to run, an algorithm needs to run. And instead of counting, instead of using a stopwatch, we make a mathematical function that specifies how many basic CPU operations, essentially, the program's going to take. I call those basic operations. And for space complexity, that's another kind of computational complexity analysis. That's when you want to figure out, for a particular input size, how much memory is my program going to use? How is my algorithm going to use as it computes its answer? All right. So you can think of this as you're counting how many bytes it's going to take when the input's n things. How many bytes is your algorithm going to take to compute its answer? Is it going to need? Okay. So there's space complexity and time complexity. Those are the two most common ones. And the reason we count operations and we don't use wall clock time, we don't say, oh, my program took 42 minutes, is because you can run your program on your phone as well as on your laptop or your desktop. And those have different clock speeds in their processors. A 1.5 gigahertz processor is going to run the same program twice as slow as a 3 gigahertz processor, assuming they're the same type of processor. So that's why you can't really use time. We're just going to count operations, assembly instructions, kind of, if you know what that is. Okay? So, yeah, that's time complexity. Space complexity is all right, for a given input size, how much memory do I need? Do I need to make an array or a vector? How long do those need to be? In number of bytes, essentially. That's what you're getting at. And so the idea is, the reason we learn about these kinds of complexity analyses, these asymptotic notation things, is that we can come up with a number, with a function, a mathematical function, I don't know, 2n squared, that talks about how many bytes our program uses for space complexity, or how many basic operations our program takes for time complexity. That's the goal. All right. So that's our key idea, and yeah, it's all for a variable input size. That's essentially the input to your function is the size of your input. It's the size of the array that you're getting from the user, something like that. The number that your variable holds, all right? And then once you have that mathematical function, you can use all the rules that we've been using to do big omega, big theta notation, asymptotic analysis that gives you a good answer. It gives you a class of different kinds of algorithms that are all very similar. These are all n squared algorithms. These are all O of n algorithms. And that's what we care about in 41 and, of course, in computer science in general, all right? So here is one example before we leave. Let us analyze the running time of this idea of summing all the elements in a vector. All right, so here's the code. I am going to walk you through it very slowly, but it's going to take a vector of a bunch of things, and it's going to give back the sum of all those things, which is, again, just an int because it's a vector of ints. And it's the normal calculation, right? Sorry, I can't fit it all, so it's a for loop. Just visit every index, add them to a sum variable, return the sum. Let's talk about the running time. So we're going to do the running time analysis for this function, not space complexity analysis, running time analysis. And so we want to come up with a formula, a mathematical formula based on n, which is the number of elements in the vector, essentially, because that's what's going to be different and cause the program to take longer for different vectors. We're going to use our n, and that'll count the number of basic operations that our program is going to require to compute its answer. All right, we're going to come up with a formula for that. And I should now tell you what in the world is a basic operation. So a basic operation, let's assume that it's one of these lines. Let's call a basic operation something, it's just a simple line of code, essentially. Let's call a basic operation assignment, just to assign a value into a variable. That is one basic operation, let's say, and we're going to count these. To return something, that takes one basic operation. Plus or minus or times, some mathematical thing involving just numbers, that is one basic operation. To look up the value of a variable, that's one basic operation. Something like that, okay? You can just assume that a basic operation is just like a line of code, more or less. Maybe it's like one or two in a line of code that doesn't like call any functions or do some weird looping kind of thing somehow on a single line. But yeah, that's the idea. Most single line pieces of code assuming they don't call any weird functions that themselves loop, take up just one or a couple basic operations. That's going to be our goal. And so let's see here. So n here, we're going to assume that's the size of our vector, because that changes. That's going to be the different thing. We don't really care about the contents, but the size of the vector tells me it's going to be different. It's going to give us a different speed, right? If the vector is small, it's going to take not too long to sum all its values, but if the vector is huge, it's going to take a while. So n is the size of the vector in this example. And let's count all of the basic operations in this code. And it doesn't matter if you don't get the same count as me, because you can drop off constant factors. But I'm going to try and be as precise as possible. So here's our v. We're given v, and it's of size n. All right. So we have, let's see here. We have a line that involves assigning a value into a variable. And so that takes up, that's a single assignment. Put the 0 into sum. That takes up one basic operation to do that line. Okay. And now, on this next line, we are going to set n to whatever the result of v.size is. Let's assume calling v.size, it does constant work. Let's say that's one basic operation to call v.size, get back an answer. So we have that answer, that's one basic operation, and then another basic operation to put it into n, because that's your assignment statement. Okay, so that's going to be two basic operations. And then we do this for loop. Okay, so now we have to think about the for loop. Hard. What in the world do we need to do here? So we need to set I to be 0. That's going to take one basic operation. And this line is only ever going to happen once, right? That's the initialization part of the for loop. So that only happens once. But the rest of these, right, they're going to get looped. So all of these bad boys are going to get looped a number of times. And we need to figure out, like, how many times eventually. But let's just deal with, like, what is how many basic operations on this particular line for the comparison of the loop. It's, well, look up the value of I, look up the size of the vector, 2, plus one more for compare those results once you have them. So that's going to be 3 basic operations on this line. I++, remember that is secretly I equals I plus 1. So it's going to be like look up I, add it to 1, set the value of I. That's another 3 basic operations, let's say. And then finally, we need to go to v at I. Let's assume that also takes one basic operation. And then add that result into sum. So v at I, sum equals sum plus v at I. So look up sum, call v at I, add them, put the result back into sum. That's 4 basic operations in total. And how many times is this going to loop is the main question. Well, it's got to do the comparison, the body, I++, as many times as I ranges, right? So I is going to go through every valid index of this vector, and there are n indices. So this is going to repeat n times. Plus an extra time for the comparison, because the comparison needs to be false once more to stop the loop. So remember that. And then it returns sum at the very end. So that's look up the value of sum, and to return it, that's going to be that one and that one. So 2 basic operations on that line. All right. So that's our analysis. And let's count the number of basic operations now. Again, you drop constant factors, so you don't have to be precise like I was. But this is why you don't have to be precise. We're going to do it in full once at least. So what's the number of basic operations for running this code on an input of size n? So it's just the sum of all the basic operations inside the whole body. So there's 1 plus 2 from this line, it only happens once, plus 1 from this initialization line, plus n times, do all these things, 3 plus 3 plus 4, and then a for loop. It needs to check its condition one last time to stop it, so the n plus 1th time, it's going to do another comparison, which is 3 basic operations to stop the loop, then it's false. And then it returns sum, which is 2 basic operations. And so if you convert all this now, the mathematical function that defines how much work, how many basic operations we do given a size n vector, that is 4, 5, 6, did I do that wrong? 5. Okay, 5 plus 5. 5 plus 5 is 10. No, sorry. I'm going crazy. I think I did it wrong last time. This is 9. 5 plus 4 is 9. And so that's 9 plus how many n's? That's the 10. So that's 10n. I knew I had a 10 somewhere. 10n plus 9 basic operations. And that depends on n, of course. And that n looks weird. Let me redraw it. Okay, so that is your f of n. And of course, we can analyze this, get the tightest possible bound, to know that this is a linear time algorithm. This is big theta of n. Okay? And that is our analysis. That's, if you want to be extra precise, you have to go through this ridiculous amount of effort. But because you don't have to really worry about the constant factor, you're going to drop that anyway, you can just assume, like, that's constant. That's one. That's one basic operation. This is just one basic operation. This is just n times a bunch of constant stuff, right? Because you're going to drop the constant anyway. It all works out to be, big theta of n. And that's why. Okay? So hopefully me walking you through that gets you better intuition for why you can just kind of like glaze over or gloss over the real counts of all these things. That I'm sure you've been doing it that way since you learned it in 41. But that's the real reason why it all works out. And yeah, that's my last example for the day. So I think that's where I want to leave you. We'll come back later and continue with all this fun stuff. But that is a taste of algorithm analysis for now. So we'll see you next time with more of this.